Topic Notes 2.5 Upwelling, El Nino, and Tropical Cyclones. This is a radar image of Hurricane Irma in September of 2017. If you were living in Florida at the time, you probably remember it because it went sort of straight up the middle of the state. Hurricanes are something we definitely deal with consistently from year to year, either watching for them, planning for them, or experiencing them. And so this note set is all about some of those various different marine-related phenomena. We're going to talk about upwelling, which has a lot to do with nutrient cycles in the ocean. El Nino, which actually has a huge impact not only in the Pacific Ocean, but also ramifications in the Atlantic. And of course, tropical cyclones as well. So let's get started. Of course, we need to get those main ideas, so here they are. Upwelling causes nutrient-rich water to reach the surface and increase marine productivity. Fluctuations in global wind and precipitation patterns can cause periodic and annual events such as El Nino. And tropical cyclones are formed by intense low-pressure systems and can cause major damage to human populations and the environment. Now, upwelling is a really important concept, and we're going to talk a lot about that when we discuss marine productivity later on in the course. But essentially, it's movement of cold, nutrient-rich water from the seabed vertically to the ocean's surface. And it can be caused in a couple of ways. One of the most common is when winds force water away from a coastline, creating a low-pressure zone that brings up colder water from the deep. This is actually demonstrated in the graphic below, where you can see again that water movement offshore and the cooler water bringing that nutrient-rich water up to the surface. Now, another option is using mid-ocean ridges and seamounts as a bit of a ramp to deflect currents towards the surface. So that happens as well. Now, upwelling, why it's so important is it acts like fertilizer to the surface waters and increases productivity. It's bringing up phosphates and nitrates and things like that that are very much needed. And it supports healthy ecosystems with high biological productivity and diversity. On this graphic, you can see on this map, all of the red areas are areas that are affected by upwelling. And they essentially support some of the most important fisheries in the world. A great example of this is the Peruvian anchovy industry off the coast of South America. It actually yields a greater catch than any other single wild fish species in the world, with annual harvests varying between 4.2 and 8.3 million tons between 2008 and 2012. So this is a really important, not only for the fish being sold in markets and stuff, but from the economy of South America. Now, this brings us to El Nino Southern Oscillation, which is something that occurs every 3 to 5 years, sometimes up to 7 years in gaps. And it's a weather pattern that affects the Pacific, and it changes things, including that upwelling we were just talking about on the coast of South America. And it has some major ramifications. So let's get into it. So first things first, we need to understand what the normal conditions are that actually support upwelling and all of the good productive fisheries that we know of. So in normal conditions, we have something called the Humboldt Current, which is a cold water current with a low salinity levels that flows north along the western coast of South America, bringing cold water towards the equator. Now, this is the current that generally not only brings that cold water, but also kind of supports that upwelling that occurs along the coastline there. Now, under normal conditions in South America, there's the strong southwesterly winds that blow the water away from the coast. And again, that allows that cold, nutrient-rich water to move towards the surface. That causes that upwelling. We also causes a high level of productivity in that equatorial South American region, which supports the fisheries that we were talking about. And on the graphic on the left, you can see that strong Peruvian current, which is involved in the Humboldt Current, and that pushes, with the upwelling that occurs, all of that warmer water way to the west. Now, if you look on the right, the bottom right, you'll notice, look at that thermocline angle and how that upwelling is occurring towards the coast of South America. That's an important graphic to pay attention to as we move forward. Now, if we look at the flip side over near Australia and Asia, The westerly winds are pushing all that warm water towards those areas, and that warm water evaporates and it provides a lot of rain. That's really important for Australia and Asia for their agriculture, things like that. And that keeps the eastern Pacific, over on the South American side, much drier. Water levels are also about a half a meter higher in the western areas around Australia and Asia compared to the eastern Pacific. Now, what we just described is what's normally happening. Now we're going to talk about the El Nino. That's the change that occurs. Now, El Nino is a warm current that develops off the coast of Ecuador around December, which can cause a widespread death within local food chains. And we'll get into why that is as we go along. So now let's look at El Nino conditions, this periodic 3 to 7 year cycle, right? The prevailing trade winds change or decrease in magnitude, preventing the warm water from moving west. Essentially, that means the warm water builds up along the east and it stops the upwelling that usually occurs due to that Humboldt Current moving through. Take a note of the thermocline on the image to the bottom right. Notice how it's much deeper towards the South American coastline, so you don't have it coming up. You don't have that upwelling coming up anymore. Now, without that upwelling, the productivity declines and the fisheries crash. Also, on the Indonesian and Australian side, they experience drought conditions, which is really bad for them. Peru and the eastern Pacific experience more rainfall than they're used to getting, so sometimes that can cause floods and landslides. Now, of course, with one thing comes another. There's also something known as La Nina, which is a cold current that develops off the coast of Ecuador and spreads across the Pacific, reducing sea surface temperatures for extended periods of time. This generally occurs after an El Nino event, so it's sort of like the pendulum swinging the other way more dramatically, and it brings additional upwelling, nutrients, and productivity to the area. It's generally marked by 3 months in which the sea surface temperature is 3 to 5 degrees below average. And again, it also, which is interesting, it leads to increase in hurricane activity in the Atlantic basin, which is interesting. Now, overall, when we talk El Nino specifically, we're still working on it. The actual mechanisms to why it happens and the periodicity of it is still a little bit of an unknown factor for scientists, but we continue to monitor and track it because these are incredibly complex systems that cause the various variables that trigger these sorts of events. Now, El Nino is identified as 3 consecutive months where the equatorial Pacific sea surface temperatures are over a half a degree Celsius above normal. And it wouldn't seem like a half a degree is a big deal, but it really has huge ramifications for the way the water is delineated and flowing and density gradients, things like that. The strong events of the recent past, there's the 82 to 83 event, which was a temperature difference of about 2.1 degrees Celsius. Flooding in the Eastern Pacific Basin was a really big issue. The 1997-98 El Nino had a temperature difference of 2.3 degrees Celsius, which was the strongest event on record until 2015-16, which essentially equaled it in strength. All right, now it's time to talk about something that's near and dear to all of our hearts because we have to deal with them every year during hurricane season, and that is tropical cyclones, often also called hurricanes and typhoons. A tropical cyclone is a localized, intense low-pressure wind system that forms over tropical oceans with strong winds. And this is a radar image of Hurricane Irma, but if you want to look at some of the more kind of larger magnitude storms over the years, I have a chart there on the right, and you can see where Irma lies up with that, with maximum winds of about 175 miles an hour, all the way up to Hurricane Allen in 1980, which was 190 miles per hour. And of course, you can look at things like Katrina, 175 mile an hour winds, 2005. We know about that. Hurricane Andrew in 1992. And you'll also notice their pressure on the far right column there, the minimum pressure. You'll notice that generally the lower pressure, the more powerful the storm is. And there's a reason for that as we go. So let's keep figuring it out. So let's start with the formation of these storms. You need a large body of warm water, specifically with temperatures higher than 26 degrees Celsius. Now, see, you knew all about this because you know hurricanes don't form over lakes. They need those large ocean basins. And if you look at the graphic here, it'll show you some of the areas of formation globally. And we'll sort of center on the Atlantic, where you're looking at just above the equator, off the coast of South America, kind of in the middle of the Atlantic. That's where these depressions and these waves start to form, and then they move in towards land. You have some that take that northern track up towards Florida and the eastern seaboard of the U.S. Others go straight across the Caribbean into the Gulf of Mexico, and others into the Central America region. Now, that warm water is going to cause warm air over that warm water, and that warm air has lower density. And on top of that, it's being loaded up by a water vapor through evaporation. This creates a low pressure area, which would eventually form and be called the eye of the storm. Now, cooler air is drawn in from the sides as warm air rises, and that creates that wind. Water vapor will condense as it rises, releasing large amounts of stored energy called latent heat. Now, this increased heat energy fuels the storm, causing more evaporation and stronger winds, and it just keeps amplifying and feeding itself as it goes, again, as long as it has that warm water under it. Now, the system also begins to spin because of the Earth's rotation and the Coriolis effect. Now, this is also why you don't have formation right on the equator, because right on the equator, the Coriolis isn't going to really affect it much. You need to be just offset from the equator where you start to get the effect of the Coriolis effect on either side of the hemispheres, if you will. Now, these prevailing winds will then direct those storms in rather predictable patterns. That's why initially I showed you that diagram where it showed these are the major paths that we see. And different times of year, you'll have more of a prevalence of one path over another. But again, these are very complex meteorological systems, so they can change and be a little different from time to time. Now, living here in Florida, you probably have a pretty good idea of the impact of hurricanes, right? High winds can destroy coastal property for sure. Flooding in low-lying areas is a huge issue. It can cause property damage and drownings. In fact, a lot of people do die from flooding more than winds, and that ties into waves and storm surge specifically, which can erode shorelines, damage moored vessels, and push water inland and add to the flooding, which again can be a life-threatening issue. Now, what we don't always think about is the impact on the environment. Now, erosion of shorelines, dunes, and loss of coral reefs can all be problems for environments as the hurricanes come through. Heavy rainfall in dry areas can actually do more beneficial things like support future growth and recovery of ecosystems. Storm surge can carry nutrients into coastal waters, which increases productivity, which can be a good thing in certain areas, and it can maintain successional diversity. Essentially what that means is it can knock the ecosystem down from a climax situation and allow plants that can't grow in climax communities to grow a little bit and other animals to be involved in that. So it can actually have a beneficial situation there. Also with reefs, it can break some of the coral off, especially the branching coral, and redistribute those fragments where they can grow elsewhere. But of course, there's some negative things like this poor little manatee that got stuck on land after a storm. That I think it was over on the west coast of Florida. So hurricanes are a mixed bag of things. They can actually help clean out a system. It can help redistribute things and nutrients, fragments of corals, things like that. But they can also be very damaging too to the environment. So kind of back and forth, especially when you add human environments on and habits onto this. For example, if you have a lot of nutrients in the waters because of agriculture and city runoff, and you push all of that out into the water, that's going to cause a bigger problem for the environment. So there's definitely some give and take there. All right, we are back to our main ideas here to wrap things up. Upwelling causes nutrient-rich water to reach the surface and increase marine productivity. And of course, fluctuations in global wind and precipitation patterns cause periodic and annual events such as El Nino. Tropical cyclones are formed by intense low-pressure systems and can cause major damage to human populations and the environment. All right, that is all for us this time. Until next time, keep learning.